Stream ecosystem ecologists have creatively adopted metrics from reactive transport theory for the quantification of nutrient spiraling. In particular, the uptake length, uptake flux, and uptake velocity metrics have been widely used in comparing streams to test hypotheses about the controls on nutrient processing. You may have seen these metrics depicted on the vertices of a triangle, as shown in this figure from Webster and Valett used in the book Methods in Stream Ecology. However, I think this diagram is missing an opportunity to provide a spatial context that might help in interpretation of these metrics. For example, maybe some sort of bivariate organization can delineate regions of the space that define the logic underlying reactive transport parameters. We have found that common themes in the dimensional analysis of the derivation of these metrics provides a useful grid for categorizing the space. Rows are defined by 3 of the dimensional reference frames commonly used across reactive transport research. Namely, the rows describe the effective reactions occurring within the volume of mixed reservoirs, the effective reactions occurring along the length of flow paths, or the effective reactions occurring across reactive surface areas that are in contact with flowing water. Columns in the space define either the absolute capacity of a reaction to consume reactant mass, or the relative efficiency with which a reaction can alter the fraction of reactant concentration remaining. Finally, a whole system Domkoehler index of efficiency can be defined in each reference frame. This metric characterizes the likelihood that solute will be processed before export from the system. By the end of this talk, I hope to convince you this is an appropriate and useful organization of reactive transport reasoning. But to do so, I will need to build the logical scaffolding from the basics of a mixed reservoir. The mixed reservoir reference frame can be built from fundamental dimensions by first characterizing the amount of space occupied by the reservoir, which I'll arbitrarily conceptualize as a rectangular prism. The fundamental dimension of space is the length of a line, such that a volume of space turns out to have derived dimensions of length cubed, or the product of 3 lengths in orthogonal directions. Mass is a fundamental dimension describing an amount of matter. We might use mass to describe the amount of solutes within the reservoir. But the abundance of a solute is more likely described with derived dimensions relative to a given volume of water in the reservoir. This provides a metric of concentration that has dimensions of mass of solute per volume of solution. We call this a mixed reservoir to simplify the math and logic by assuming the solute is uniformly distributed throughout the volume. This collection of related derived dimensions illustrate why we are calling this a reference frame. A reference frame is a derived dimensional construct that allows quantification of a given conceptual model for system structure and function. The idea of reference frames was perhaps most famously used by Einstein in describing the special theory of relativity, though we perhaps use a more liberal definition of the term here. The quest for transferable dimensional reference frames goes back at least to the principles of Newtonian mechanics and has been directly promoted by the likes of John Strutt or Lord Rayleigh through the pursuit of similitude. To quantify the effect of a chemical process on a solute, we need a new dimension that allows descriptions of the rate of causality. The fundamental dimension of causality is time, and a reaction rate is often defined as the rate of change of a reactant concentration with respect to time. Carrying the dimensions of concentration and time through this calculation defines the dimensions of a reaction rate as a mass of reactant per volume of solution per time. These dimensions illustrate why we might categorize the reaction rate metric as an absolute effect of a reaction on a reactant mass in a mixed reservoir. We can define a metric of reaction efficiency for a mixed reservoir by building on this logic using chemical kinetic models. Let's consider a reaction that is strongly limited by the probability of reactants encountering each other. In this case, a first-order chemical kinetic model would suggest the reaction rate is directly proportional to the concentration of the reactant. Solving this ordinary differential equation predicts an exponential decay in the fraction of the reactant concentration remaining over time. The proportionality constant for first-order kinetics is called the rate coefficient or rate constant, and rearranging the algebra shows it is the reaction rate normalized to the ambient concentration of the reactant. Therefore, the dimensions of the rate coefficient simplify to the inverse of time, which comes from the dimensionless fraction of the ambient reactant concentration being processed per unit time. A reaction rate normalized to the abundance of a reactant is a key indicator of a metric of efficiency. A more efficient reaction will either have a higher reaction rate for the same ambient reactant concentration, or a more efficient reaction will be able to maintain the same reaction rate with a lower abundance of the reactant. We can round out the metrics for mixed reservoirs by characterizing a whole reservoir efficiency that describes the likelihood of a reactant being processed before export. The inflow and outflow of the mixed reservoir have dimensions of a volume of water transfer per time. To keep the math simple, we'll assume a steady state condition where the input and output flows are the same. The inflowing water will have some concentration of reactant. Assuming that inflow instantly mixes with the entire volume, the output concentration will be the same as the uniform concentration within the mixed reservoir. The average residence time under steady state conditions is defined by the time it takes the volume of the mixed reservoir to turn over relative to the input or output flow. A Domkohler number for this mixed reservoir might be defined as the dimensionless product of the rate constant and the average residence time. The Domkohler number is a metric of whole system efficiency because it allows us to think about the influence of a reaction relative to the amount of time the solution is subject to that reaction within a system of interest. Rearranging the conservation of mass equation for this flow-through mixed reservoir reveals that the Domkohler number has an inverse hyperbolic relationship with the fraction of the input reactant concentration remaining in the system output. An inverse relationship with the fraction of input concentration remaining, or a positive relationship with the fraction of input concentration consumed, is exactly what you would expect for a metric related to whole system efficiency. A flow path might be characterized as a sequence of parcels of water, each representing a mixed reservoir in motion. The need to add a longitudinal length to the flow path reference frame comes from recognizing that these parcels of water in motion do not fully mix with each other. And the reactant concentration in outflow is therefore defined by the altered chemistry of parcels of water after they have traveled over the length of the flow path. The mass of reactant in transport might be defined as the amount of advected solute passing through a transect of the flow path, where the extent of the transect is defined by cross-sectional area of flow. This mass advection rate is a metric often called load, which is a mass of reactant transfer per unit transit time that can be calculated from the product of the volumetric flow and concentration. The concept of load allows the definition of a longitudinal reaction rate, based on the change in load with respect to distance x along the flow path. The dimensions of a longitudinal reaction rate are thus the mass of reactant consumed per unit transit time per unit length of the flow path. After recognizing some geometric identities, the longitudinal reaction rate turns out to be the product of the cross-sectional area of the flow path and the temporal reaction rate occurring within parcels of water traveling the flow path. This relatively simple geometric adaptation of the temporal reaction rate demonstrates this metric's utility in characterizing the absolute reaction effect on parcels of water in a flow path. In fact, we will see that all metrics in this column can be related to geometric adaptations of the temporal reaction rate, and, spoiler alert, all metrics of efficiency can be derived as geometric adaptations of the temporal rate coefficient. On that note, a metric for the efficiency of reactions occurring along a flow path can be derived with a space for time substitution. Assuming steady-state plug flow conditions without longitudinal mixing, travel of parcels of water along the length of the flow path will be associated with a single characteristic transit time, determined by the average velocity of flow. The average velocity provides a dimensional map from a transit time to a distance traveled along the flow path. A longitudinal reaction rate coefficient can be derived by dividing the temporal reaction rate coefficient by the average velocity. This space for time substitution dimensionally translates a fraction of reactant concentration processed per unit time to a fraction processed per unit length of flow. The exponential decay of reactant concentration in parcels of water over time therefore translates to a steady-state exponential decay observed over the length of the flow path. Ultimately, the uptake length is the inverse of the longitudinal rate coefficient, characterizing the length of the stream necessary to reduce the reactant concentration to about 37% of the initial value. The positive relationship of the longitudinal rate coefficient with the fraction of ambient reactant concentration processed solidifies its position as a metric of reaction efficiency. An uptake length as the inverse of the longitudinal rate coefficient may thus be considered in this general category as a longitudinal metric of inefficiency. Again, using space for time substitution, the advective Domkohler number might be defined as the product of the longitudinal rate coefficient and the length of the flow path. This Domkohler number is effectively a dimensionless ratio of lengths, which is more evident in recognizing it as the quotient of the length of the reach and the uptake length. The Domkohler number is again inversely related to the fraction of input reactant remaining, in this case via an exponential decay function. This relationship again demonstrates the Domkohler number's ties to reaction efficiency in the sense that a higher Domkohler number means a larger fraction of reactant processed by the system. The value of the Domkohler efficiency for a flow path will not be different if it is calculated with respect to time or distance along the flow path. However, use of the longitudinal derivation provides an alternative perspective in that it represents the number of uptake lengths that you can fit within the length of a flow path of interest. Finally, the reactive surface reference frame is an extension of the flow path reference frame. The reactions that are affecting the flow path may not be occurring throughout the entire volume of mobile water. They may instead be occurring across an area of reactive surface that is in contact with the mobile water. The reactive surface reference frame is particularly useful in streams because most biological activity is happening in proximity to the stream bed. And thus, in stream ecosystem science, we commonly want to compare the intrinsic capacity of stream beds to process nutrients. Describing the extent of the reactive surface area requires defining an average width orthogonal to the length of the flow path. A summary of the distance of the channel water from the reactive surface is defined as an average depth, which is either locally the cross-sectional area divided by the width, or generally the volume of the flow path divided by the reactive surface area. The intrinsic effectiveness of the reactive surface is characterized by fluxes of either solute mass or water volume across that surface. Fluxes are defined dimensionally by the areal density of transfer of energy or matter per time. I cannot stress enough the importance of the per area in these dimensions for their proper interpretation. The fact that these metrics represent areal densities means that we have inherently lost information about the total amount of mass or volume transfer. Therefore, these metrics help us compare the behavior associated with an average square meter of the stream bed rather than the behavior of the stream as a whole. The absolute effect of the reactive surface on reactant mass is defined as an imagined mass flux of reactant across the reactive surface. We are already most of the way to the dimensions of a mass flux with the change in reactant load per unit distance of flow. Dividing the longitudinal reaction rate by the average width yields the dimensions of a mass flux of reactant across the reactive surface. Further geometric tinkering reveals that this metric is the product of the average depth and the apparent reaction rate if it was applied to the flow path. And perhaps it is quickly evident this mass flux is what the stream ecology community calls areal uptake. A metric of relative efficiency of a reactive surface arises from imagining a volumetric flux of water that would be necessary to explain the observed loss of reactant mass. A mass flux of solute can be converted to a corresponding volumetric flux of solution simply by dividing by the concentration of the solute. Dimensions of this formulation also emphasize how this metric describes the relative effect of a reaction on a fraction of the ambient reactant concentration. Even more algebraic tinkering demonstrates this metric is the product of the average depth and the temporal reaction rate coefficient, suggesting it is a relatively simple geometric adaptation of the temporal reaction efficiency. This volumetric reaction flux is what a stream ecologist would call an uptake velocity, meaning the uptake velocity is telling us how much the average square meter of the stream bed is able to reduce the fraction of reactant concentration remaining in the flow path. I'd like to emphasize one more time that metrics in the reactive surface reference frame represent an intrinsic property of the stream bed rather than an aggregate capacity of the whole stream. Note that these metrics will indeed have higher values if the absolute or relative reaction effect on the reactant is higher, as indicated by a higher temporal reaction rate or rate coefficient. However, these metrics will also have higher values if the same absolute or relative reaction effect on a given volume of water is being provided by a smaller reactive surface. We can also define a Domkohler number with respect to an average square unit of the reactive surface rather than the whole flow path. The hydraulic load provides a characterization of the loss of reactant in export in the same dimensional context as the volumetric reaction flux or the uptake velocity. Specifically, the hydraulic load can be imagined as the volumetric flux of water across the reactive surface that would explain the amount of solute loss and export from the downstream end of the flow path. The Domkohler number can then be calculated as the ratio of the volumetric reaction flux or uptake velocity to the hydraulic load. This derivation is again a dimensionless ratio, but this time it is a ratio of the volumetric flux describing reactant loss to chemical reaction versus the volumetric flux describing reactant loss to export from the system. This formulation demonstrates how the Domkohler number for a reactive surface system is the same thing as the Domkohler number for an average square unit area of the reactive surface. We hope this dimensional analysis provides a useful mapping of nutrient spiraling metrics to more general principles of reactive transport. We suggest that dimensional analysis is a universal epistemological tool that provides a clearer logical pathway to understanding the meaning of these metrics. Given the need to understand the controls on geophysical interactions between organisms and their environment, perhaps dimensional analysis could use more attention in the pedagogy and research products of ecosystem science.